Welcome back to our Calculus 3 class notes. We're on page 56 and we're still in chapter 14 on partial derivatives, and we're working now into section 14.5 where we're going to talk about directional derivatives and gradient vectors. So first of all, the directional derivative. The partial derivative of f with respect to x at a point x naught y naught is the derivative of z equals f of x and y at the point p naught, which is x naught, y naught, in the direction of I. So if you look down at our drawing here, so when I draw this, this is sort of, I like to kind of call this Herbie the Whale. I think I told you in the story in class at one point. But it's just a generic surface. So this is z equals a function of x and y. So the point x naught, y naught down here in the xy plane is right here. And z equals f of x naught, y naught is right here on the surface of our, right on the outer surface of our surface. Okay, so if I want the direction, if I want the derivative in the direction of I, that is the partial derivative of f with respect to x. Okay, so in the direction of I, which would be parallel to the x-axis, that would be the slope of a tangent line right on the surface here. Now the partial of f with respect to y at that point is the derivative of z but in the direction of j. So that would be parallel to the y-axis. That would be the slope of a tangent line sitting on the surface right here. Okay, but if I want the derivative in any other direction, I have to look at that as a combination of those two derivatives. Right? It's some distance in the I direction plus some distance in the j direction. If I add those two vectors together, I get u, which is the direction of the derivative that I want. So the tangent line that lies in that direction that touches the surface. Okay, so all it is a combination of so the notation is d sub u of f. We say the derivative of f in the direction of u is the partial of f with respect to x times u1, which is the I component of the vector that gives the direction, plus the partial of f with respect to y times u2, which is the j component of the vector that gives the direction. So in the direction of u, that's how you compute the directional derivative. And you can see I've written those things down right here. So what is that? It's the dot product of the direction vector that tells me which direction I want the derivative, which is u1i plus u2j, with this vector, which is the partial of f with respect to x evaluated at the point in the I direction, plus the partial of f with respect to y evaluated at that point, x naught, y naught, in the j direction. So it is the dot product of these two vectors. Now, that brings in a definition. So this vector right here is what is known as the gradient vector of f. So the gradient vector of the function f of x, y at a point p naught, x naught, y naught is this vector, and this is just a definition. So usually we say the gradient of f or grad f, some people short that, and this notation is the upside down delta. So this is this notation, and when you see it in type, it's usually just a bold, a symbol like this. But since I can't put a bold with my handwriting, I got an arrow over it. Right, just like because it defines a vector, right? It's the partial of f with respect to x in the I direction plus the partial of f with respect to y in the j direction. Or if I use my bracket notation, it's this brackets with f sub x, f sub y. Okay, so the directional derivative, the derivative of f in the direction of the vector u, is grad of f dotted with u. And of course, these are evaluated at x naught, y naught. So let's look at an example. Example 52. We want to find the derivative of f of xy, which is x times e to the y, plus cosine of xy, at the point 2, 0, in the direction of v, which is 3i minus 4j. So I specifically use v here because I'm going to change that to unit vector. Whenever we say we want the derivative of f in the direction of u, we mean u is a unit vector. So if it's not given to you as a unit vector, you have to make it a unit vector. Otherwise, the formula doesn't work. So to make a vector a unit vector, you just take it and divide it by its own length. We've done that a lot before. So 3i minus 4j divided by the length of 3i minus 4j. To find the length, you just square the components, add them up, take the square root. So 3 squared plus negative 4 squared gives me 9 plus 16 is 25. The square root of 25 is 5. So that gives me 3/5 in the I direction minus 4/5 in the j direction. So that's u. So now I need to find the partial of f with respect to x and the partial of f with respect to y. So that's going to be partial of f with respect to x is just e to the y. And then minus y times sine of xy. And partial of f with respect to y is x e to the y minus x sine of xy. Evaluate each of these at the point 2, 0. I get e to the 0, which is 1, minus 0. And then 2e to the 0, which is 2, minus 2 times 0. So that's 0. So I just get that the partial of f with respect to x in the direction at the point 2, 0 is 1, and the partial of f with respect to y at the point 2, 0 is 2. So the gradient of f at 2, 0 is 1 and 2, right? So it's 1i plus 2j. And the derivative of f in the direction of u at the point 2, 0 is a gradient of f at 2, 0 dotted with u. So it's the vector 1, 2. That's a gradient of f dotted with 3/5 minus 4/5. So it's 3/5 minus 8/5, which is minus 1. And remember what that means is that is the slope of the tangent line sitting on the surface of f in the direction of u over the point 2, 0 in the xy plane.